The solid wood door shown in the figure has a length L, a width W, and a mass M. The axis of rotation is on the left side of the door, where the hinges are located. And part A, this is the only part that's different for AP Physics 1 and AP Physics C. In AP Physics 1, you just have to use the table of rotational inertia formulas to get the rotational inertia of the door. And so you can match it. If you look at the table in your notes, you can match it to the fourth picture, and where it has an A and a B on the picture, and try to match up and see if you can get the formula from that. For AP Physics C, you have to derive the formula using calculus. So if you're in AP Physics 1, you can skip ahead probably about a minute or so while I'm going through this derivation. So the derivation is the inertia. We're going to start off with the usual formula, which is the integral of r squared dm. And this time we're going to take an area integral rather than a volume or a linear integral like we did in the two examples in the class notes. So let's take this door and just divide it into a whole lot of these really thin strips. And we'll say that each strip has a width dr, that's an infinitesimal width dr, and then they each have the length L, the same as the length of the door, and each strip has a mass dm. Because it's an infinitesimally small strip, it has an infinitesimally small mass. So if I look at the areal density of the door, that's like saying the mass per area instead of the mass per volume. The total mass divided by the total area of the door is going to be equal to one of those infinitesimal masses divided by an infinitesimal area, which is going to be the length times the dr. And we can actually replace the area of the door, this capital A right here, we can say that that's just L times W. So we can write an LW in its place. That way we see that one of those L's cancels out. And now if you take this formula, rearrange it for dm, and plug it into there, and then integrate from basically 0, where the axis is, over to W as your limits of integration, you should be able to get to the final formula, which is 1/3 mw squared. So that's your answer for part A. Part B. Instead of using the doorknob, a man opens the door by applying a perpendicular force on the door of constant magnitude F at a horizontal distance of 2/3 of the width of the door. So somewhere around like right here, about 2/3 of the width of the door from the axis of rotation. And we want to derive an expression for the angular acceleration of the door. So Newton's second law in rotational form, when you rearrange it for the angular acceleration, is the torque, the net torque, in this case is just that one torque, divided by the inertia. The inertia formula we have, that was just that one from up here, so that's all you got to plug in for I. And for the torque, he is applying a force F at a distance of 2/3 W, and it says it's perpendicular, so that would be sine of 90 degrees, which is 1, so we don't have to put that on there, and we divide that by what's down here, and then we just cancel some stuff out, and you should get the final answer of 2F over MW. For part C, so if instead of opening the door with an angular acceleration, like we just saw for it, let's just say that there's a woman on the other side of the door who prevented the door from opening by applying a counteracting torque. And we just want to figure out, and she's applying it right at the center of mass of the door. So in other words, the distance from the hinges, or the axis of rotation, would just be W over 2, 1/2 W. So we just want to set the two torques, the torque from the man and the torque from the woman, we want to set them equal to each other. So we'll say the net torque equals 0, which is like saying the clockwise torques is equal to the counterclockwise torques. One of these people is applying a clockwise torque, one is applying a counterclockwise torque. It doesn't matter which is which, because we're going to set them equal. The man's torque is F times 2/3 W. The woman's torque is a different value for F. I'm going to call it F woman, because that's what we're solving for, times her distance from the axis, which was 1/2 W. Now you can see the W's on both sides cancels out, and you just want to solve for the force exerted by the woman just by multiplying by 2 to get rid of that 1/2. And that'll get you your answer of 4/3 F, or 4F/3. Alright, part D. So a second solid wood door made of the same material has the same width and thickness as the first door, but twice the length. And you want to figure out how many times greater is that door's rotational inertia than the first door. So if we go back to this formula again, you can see that that does not depend on the length of the door. So changing the length wouldn't affect it in that sense, but it will make the door twice as massive, because now it's just a much longer door. So it's kind of like just doubling the mass of it. So if you take this equation and just double the mass in that equation, it's just going to double the inertia, because that mass is not squared or anything. It's just a term that we can just say times 2. That means the inertia increases by a factor of 2. But in part E, if instead of doubling the length of the door, we're going to double the width of the door, so now we're kind of increasing the door in that direction, where the arrow is, and I'm going to go off the tablet screen here. But let's just say that part I'm drawing there was double the width of the door. Well, that's still going to double the mass of the door, so the mass is going to be twice as much, but it also is going to affect that W in the inertia equation, and that W is squared. So this new one is going to have twice the mass, but it's going to have twice the width, which is squared. So it's 2 times 2 squared, which is 8 times as much inertia for that door.